All right, so this lesson we're going to dive a little bit more into actually finding an estimation interval. We're going to be checking conditions, and we're going to be actually doing some formulas and some computation to come up with that interval that will capture the true proportion or mean of the population. And today we're going to be focused on proportions. 8.3 does the exact same thing, it just does it with means. The beginning part of your notes, I believe, are filled in for you, and so you don't have to do tons of writing. So what you need to make sure is that your brain stays focused on what we're doing, even though you're not having to write anything down, so that when it comes time for us to do a problem from scratch, you are armed and ready to go. All right, here we go. Before constructing a confidence interval for p hat, you should check some important conditions. Random, independent, and large counts condition. And these are the three conditions that you're going to have to construct for every single interval you do, whether it be proportions or means. You're going to have to tell me that it's random and tell me how you know. You're going to have to do the independent, the 10% condition, and you're going to do the large counts, and the large counts is what tells you that it's normal for proportions. So when we switch to means, obviously you're not going to do the large counts. You're either going to tell me that the mothership was normal or the CLT grants you normalcy. So this condition is to show that it is normal, and for proportions, that's the large counts condition. All right, so for something to be random, it's going to either say it in the not either. It's going to say it in the problem. It's going to say that it came from a simple random sample, or that a random sample was taken. And what I recommend doing on an actual FRQ where you are writing and turning it in like you're going to be doing on the exam, I would underline in the problem where it says that. Again, you're communicating to the grader that you see that and you know that it's important. So for that condition, you're just going to write the word random, and you're going to put a check mark, and you're going to put simple random sample, or you could say stated in problem. And again, you have underlined it in the problem. So you are acknowledging that that condition has to be met, and then you're saying, yes, it has been met. Independent, you're going to write the word independent. You're going to put a check mark, and then you're going to do the 10% condition, and you're going to write out 10% condition, and then you're going to write the formula, and then you're going to plug in your data. And then your last condition is that you're normal, so you're going to put a normal and then a check mark, and then you're going to say, okay, since this is proportions, I'm going to have to do the LCC. So you're going to do NP and NQ, and they have to both be bigger than 10. Now, here's the tricky part for LCC. We are finding, and this shouldn't have a hat on it, we are finding a confidence interval for P, mothership P. So you don't know P or Q. What you are going to know is P hat and then obviously Q hat. So when you do your large counts condition and you do NP is greater than or equal to 10 and NQ is greater than or equal to 10, you are now going to have to go in and put hats on this because that's not mothership information. You don't know who P is. So when you plug this in, you're going to hopefully read and understand that that is a P hat, that is sample data that they gave you, and you'll get that from reading. And so then you know, okay, well, this is sample, then I have to put hats on my P's and my Q's. Okay? All right, so here we go. And the first couple of problems just focus on checking these conditions. So it says Ms. Patterson has a container full of different colored beads. Let me turn this around. There we go. I have 3,000 beads. Your goal is to estimate the actual or the true proportion. Okay, so let's talk about that. The actual or the true proportion is mothership P. So from the population of red beads in the population. So P equals the true proportion of all red beads in the population, in the bucket of bead container of beads that I have. You take a random sample of 251 beads, that's now my little n, and you count that 107 of them are red. So guys, I now know that P hat is 107 over 251. Again, I know that has a hat on it because this is sample information. I am looking for P, okay? So the first thing we have to do is check the conditions are met for constructing a confidence interval. So I have to be random, independent, and normal. And I think I would rather this condition be called normal and then using the LCC to justify that it is normal. So random, let's see, it says it right here, random sample. So I'm going to underline that. I put it in quotes so they know that I know that it came from the problem. And then I put a check mark stating that that condition has been met. So don't make this a big, long, drawn out thing. Just say random and in quotes random sample and then a nice big check mark. And then make sure that you have underlined it in the problem. Independent, and I was bad here and did not write out my 10% condition. And then my formula. And then go, all right, so let's make sure we know where the 251 comes from before I just start writing it in here. So the 251 is your small n. That is my sample size. Little n is your sample size. Doesn't have anything to do with the red beads. It's just your sample size. So 251 is less than or equal to 1/10 of 3,000. So for this problem, I actually know what my big N is. So 251, 1/10 of 3,000. And I know that 1/10 of 3,000 is 300. So 251 is smaller than that, not by much, but it is smaller than that. So I did a crappy job there. This is what I want to see for independent. I want you to tell me that it's the 10% condition. I want the formula, plug your numbers in, and then justify it with a check mark. And then we want to be normal. To be normal for proportions, we're going to use the large counts condition, which you can just write as LCC. And I've got my NP and my NQ, and they both have to be bigger than 10, but notice that they have hats on them. And I wrote PQ. Sorry. NP and NQ, this is just full of mistakes. NP and NQ have to be bigger than 10, but those P's and Q's have to have hats on it because I don't know P and Q, but I do know my sample information. So my N is 251. My P hat is the 107 over 251, and that has to be greater than or equal to 10. This is really easy because the 251s are going to cancel. Top number falls down, and that is bigger than 10, so he gets a nice big check mark. And then this is N. All right, now this is Q because if P is 107 over 251, Q is just everything that's left over, which would be 144. Over 251, and that has to be greater than or equal to 10. The 251s cancel, and that gives me 144, which is greater than 10, and so that gets a check mark. So you have just established all three of your conditions: random, independent with the 10% condition, and LCC, or being normal with the LCC. And that is going to be your one of your very first steps every time you do a confidence interval. All right. Check whether the conditions for calculating a confidence interval for the population proportion P are met. An AP Stats class at a large high school conducts a survey. They ask the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 students say yes. Okay, so I've got my independent, or my random, my independent, and my normal. All right, random. No, this is not random. This is a convenient sample. They asked the first 100 students to arrive at school. Now think about how that's going to skew your data. If I'm talking about who slept at least 8 hours, the first 100 people to arrive to school might be the most rested, most prepared, most responsible, whatever. And then, your ones who stayed up till 3 a.m. on their phone or playing video games and slept as late as they possibly could and come in the parking lot on 2 wheels to get to first period on time. Those might be kids who are doing a poor job at getting good sleep. So this is not a random sample. So no, it is independent. And again, you're going to write 10% condition and your formula. I have 100 students in my sample, 1/10. I do not know how many people are at this school, so I write, and the all is a very important word, all students at this large high school, and we just assume that's true. And to be normal, I'm going to do the LCC, which is in P hat greater than or equal to 10, and in Q hat greater than or equal to 10. And my sample said that 17 said yes, so that's 17 out of 100. Hundreds cancel. 17 is bigger than 10, not by much. So then I have 83 who said no, and the 83 is bigger than 10, so that's good. So for this problem, it is independent and it is normal. However, it is not a simple random sample. So if this were an actual FRQ, you could not continue because the conditions weren't all met. Now, I've never seen on any test or AP exam for them to give you an FRQ where the conditions are not met and then you could not continue with the problem. So most of the time on a full FRQ, the conditions will all be met, but you still have to state those conditions. This would be a great multiple choice question saying, are all the conditions are met? If one's not met, which one is it? So looking at the third one, a quality control inspector takes a random sample of 25 bags of potato chips from the 1,000 bags filled an hour. Of the bags selected, 3 had too much salt. This is a random sample, yes. It is independent. Again, I would write 10% condition, and I would write my formula here. And I had a sample of 25. There's my 1/10, and this is the thousands of bags, so absolutely, because this would just need to be 250 for this to be a true statement. I've got thousands of bags, so all is good. The LCC, however, is not satisfied, so this is not normal. Because the LCC, again, that would be in P hat. So my N is 25. That's my sample size. We had 3 successes that had too much salt out of the 25. And when I cancel my 25s, I get a 3. And 3 is not greater than or equal to 10. So no, the LCC is not satisfied. So this sample does not follow a normal distribution. So I can't use a normal distribution to approximate the probability of whatever they're going to ask me about it. So this one fails the conditions. I would have to stop there. Okay, so that runs you through your conditions, and I just want to make sure that you understand that you have to be super diligent about writing everything out. So practice it that way so you make good habits. Okay, so now we're going to actually construct a confidence interval. And we briefly talked about this in 8.1. So it is statistic, and then plus or minus. And then I have my critical value, which you don't have a clue what that is. And then times the standard deviation of your statistic. So you know what the statistic is, and you know how to find the standard deviation of that statistic. Okay, so my statistic for these are going to be p hats. In 8.3, it's going to be x bar. And then plus or minus, there's your plus or minus. And then the critical value is z star. And that's how you say it. That's his name. His name is z star. And that's how you're going to write it. And I'm going to tell you how to find him. And then the standard deviation of the statistic, for proportions, your standard deviation is the square root of PQ over N. However, please make sure you see that these particular P's and Q's have hats on them. Again, you don't know P. You don't have population information. The only information you have is sample information. So these formulas for P's and Q's, those P's and Q's have to have hats on them because you only have sample information. So on your formula sheet, it says the square root of PQ over N. But you know that you have to put hats on them, and the graders are going to be looking for that. All right, so so the standard error, that's another way that they're going to refer to the standard deviation. I think that's pretty easy to remember. Standard deviation, standard error. On a computer printout, it's going to say SE for standard error. When the standard deviation of a statistic is estimated from the data, so your standard deviation is using P hat and Q hat instead of P and Q, that's when it's referred to as a standard error. So standard error of P hat is the square root of P hat over N. Okay, so nothing big changed. It's just some terminology that you need to watch out for. So standard error is the same thing as standard deviation when that standard deviation is made from sample information. Okay, so let's talk about how to get that critical value, that Z star. Okay, so it all depends on your confidence interval. So for this confidence interval, we're going to do a 95% confidence interval. And we talked about that dartboard. So my dartboard is going to be 95% big. And I want to know the Z's. There's a positive Z and a negative Z. And they're going to be the same number because remember, normal distribution is symmetrical. That cuts off 95%. Okay, so I am going to inverse norm. Okay, so I'm not normal CDF because normal CDF finds me the area. Just to refresh, normal CDF goes from low to high with the mean and the standard deviation. And that finds area. Well, for this one, I know my area. So inverse norm is for when you know your area and you're trying to find the numbers that will chop off that much area. You're trying to find the low and the high. Well, if you'll remember, inverse norm finds percent to the left. Okay, so if I want 95% in my distribution, that means I have 5% left outside. Well, and I have two wings that are not included in that 95%, so that 5% gets split in half. So I'm going to have 2.5% in that wing and 2.5% in that wing. So when I do percent to the left, I'm going to do this guy over here. So I have 0.025. And then for Z's, remember your mean is always 0 and your standard deviation is always 1. So this will always be a 0 and this will always be a 1. Now when you type this in, and I would love for you to pause the video and type this in, but when you do inverse norm and you do the 0.025 and the 0.1, now I have a plus or minus right here, but think about it. When you type this in, you in particular for this problem are finding the negative Z. So when you type this in, your calculator is going to tell you it's negative 1.96. And that makes sense because you're finding this one. If I was going to find this one over here, I would inverse norm, but this guy would have to change because to the left of that would be the 95% and the 2.5%. So that would be 97.5%. So 0.975, 0.1. And if I did that, I would get positive 1.96. Well, there's no sense in doing both of them. You know that a normal distribution is symmetrical. And you know that that if I put this 95% in the middle, that these two z values are going to be the same number. One's going to be positive and one's going to be negative. So when you type it in and you get this negative one, just go ahead and put that plus or minus on there. You do not need to show you finding the positive z. You can just find one of them and then put that plus or minus on it. Also want to remind you that that z-score is really, really close to a plus or minus 2. And remember we said that with the 68, 95, 99.7 rule, that 95% of my data lives within 2 standard deviations. Well, we got exactly 1.96 standard deviations holds the 95%. So it's really close to that rule. It just rolls off the tongue a little bit better to say 95% lives within 2 standard deviations instead of 95% lives within 1.96 standard deviations. So that 68, 95, 997 rule obviously is an estimate. It is a super, super close estimate. So what you've just found is the Z star that exactly, the critical value that exactly cuts off 95%. Okay, so then when you do this on your paper, you cannot just have a plus or minus 1.96. You have to state that Z star equals plus or minus 1.96. You don't ever want to just have a floating number that is not assigned to a variable. So you're going to communicate with them that you know that that Z star is a 1.96 plus or minus. All right, now let's change our confidence level a little bit. So let's say I want to be less confident. And so what that's going to do, if I'm going to be less confident, that means my dartboard's going to get smaller because I'm going to be less confident that I'm going to hit it. So if I do 80%, then I know I have 20% outside. That's going to be 10% in each wing. And again, when you know the percentage of area, you're going to inverse norm. So I'm doing percent to the left. So I'm going to find that cutoff point right there. So 10%, again, always a 0 and a 1 for Z's. And that's going to give me a negative 1.282. And so then you're going to write Z star equals plus or minus 1.282. So that is your Z star if you want to be 80% confident. But this is your Z star if you want to be 95% confident. So these are both critical values that are going to go here. It just depends on how confident you want to be, and the problem will tell you. Okay, so now that you know how to find that critical value and you know that your Z star already has a plus or minus on it, and that's where that comes from. Because I'm going to take my p-hat, my point estimate, and I'm going to add or subtract this, running out of colors, this group right here to it, and that's going to give me my interval. And p-hat sits right in the middle of that interval. All right. So now, let's look at a problem, or let's continue with the bead problem. Okay, so Ms. Patterson's class took a simple random sample of beads from a container, got 107 red beads out of a total of 251 beads. Calculate and interpret, okay? Calculate and interpret a 90% confidence interval for P. So I don't know the true proportion of red beads in this container. I do know P hat. And so I'm going to use that P hat to estimate, to give an interval that I think that I'm going to be 90% confident that will capture the true proportion of all red beads in this container. Okay, so let's do part A before we even read part B. All right, so the first thing you're going to do in part A is check your conditions, which we've already done. We were a simple random sample, we were normal, and we were independent. Okay, so we've already done that previously. So then the next thing I'm going to do for interval, and this is on your formula sheet where it says interval, and we can talk about in class where to find it if you can't see it. But this right here is written out for you on your formula sheet. So you don't have to memorize that. You do need to know what each word represents, like what it means, what goes in each place. But you don't have to, if you forget or you get stuck or you have a massive brain fart, it's right there on your formula sheet. So statistic for this problem is going to be a P hat. Again, in 8.3, when we switch to means, it's going to be an X bar. And then I have my plus or minus, and then my Z star, which we now know how to find. And then my standard deviation of my statistic. But please make sure that you see that I put hats on the P and the Q, because I do not have mothership P and Q. I do not have parameter P and Q. I have sample P and Q. All right, so my P hat is, let's see, I have 107 red beads out of 251 red beads. So that's my P hat. Then I have my plus or minus, and now I'm going to go find my Z star. So I'm going to scoot over here to the right. I'm going to draw a curve. And I'm going to write, all right, I want 90% in the middle. That leaves 10%, 5% in each wing. So I'm going to inverse norm my 5% with my 0 and my 1, because these are Z's. I type that in. That one's going to give me the negative version, but I'm going to go ahead and put a plus or minus, and I'm going to go in here and write Z star equals, because I do not want to have a floating number. So Z star equals plus or minus 1.645. You're going 3 decimal places. All right, so then I take that Z star and I plug him in right here. And then I'm going to do my standard deviation of my statistic. Now, where does this number come from? Well, he is your P hat. So all I did was took this fraction and turned it into a decimal. I'm not a huge fan of putting fractions within a fraction. You totally can. You just have to watch out how you type it in. So that one's a 0.426. So that makes the Q a 0.574. And then it's over N, and my sample size was 251. Now, I'm going to type this in because the next thing I'm going to have is my interval. So here's what I'm going to do, and I want y'all to watch me type this in. Let me see. There it is. Okay, so I'm going to do 107 divided by 251. Now, I'm going to do the minus one first, because when I write my interval, the lower number comes first in my interval. So I'm going to do the minus 1.645 and then square root of 0.426 times 0.574 divided by 251. Your calculator knows order of operations, so it should multiply the 0.426 and the 0.574 and then divide by the 251. You need parentheses when you have two things in the denominator, but not in the numerator. So then I'm going to hit enter. And again, you have to be accurate to 3 decimal places. So 0.375. So I strongly recommend you typing it in just like this, one big swoop. Don't do pieces of it and then other pieces and then try to put it together. Type it in as one big swoop, because I'm going to show you something neat here in just a second. Let me go back here. That's where that number right there came from. That is the small number of my interval. And then all I'm going to do is I'm going to use my arrow button and get up on what I typed in, hit enter, brings it back down, and then I'm just going to scoot over to that minus sign and change it to a plus and hit enter. And that just helps avoid any hitting the wrong button, typing something in wrong. So super easy. Just get up on there, hit enter, it brings it back down and allows you to edit it. So I'm going to change that to a plus. And so now I'm 0.478 for my top interval. And that's where he came from. And so now I'm going to write this nice little sentence. And this is kind of that, I called it a rubber stamp sentence in 8.1. And this is that rubber stamp sentence. So here we go. We are, or you could say I am, 90% confident that the interval from 0.375 to 0.478 captures the true proportion of, I want the word all right there, all red beads in the container. So if you could add that word all in for me. We are 90% confident that the interval from 0.375 to 0.478 captures the true proportion of all red beads in the container. In other words, I am 90% sure that P resides somewhere in there. Okay? All right, so now we're going to do one from start to finish. So this is that whole state, plan, do, conclude that you remember from way back in the day. So the first thing we're going to do is we're going to state the parameter. Okay, parameter for these problems is going to be our P. Parameter for 8.3 is going to be our mu. That we need to estimate and at what confidence level. We're going to check our conditions, which is the random, the 10%, and the normal. Then we're going to perform our calculations, and then we're going to put this interpretation, which is this nice little sentence with a bow on top. All right, before we move on, I realized that I have forgotten to do part B. And part B is just sort of an interpretation and explanation of this problem. So it says, Ms. Patterson claims that exactly half the beads in the container are red. All right, well, let's look. I'm 90% confident that the exact proportion of red beads is in that interval, which does not contain a 0.5. So you can turn your paper sideways and read my explanation for part B. So because 0.5 is not included in our 90% confidence interval, it is not a plausible value for P. We have good reason to doubt Ms. Patterson's claim. All right. So here we go. Here is a problem full out, and I'm sure I'm probably going to want to add a couple things to it just to sort of make sure that we are writing our formulas out and that we have all the words that we need. So we're probably going to tweak it just a little bit. So here we go. We're going to talk about alcohol. And I think the next problem we talk about sex. So, really good topics for today. Here we go. And I'm going to turn this. There we go. Alcohol abuse has been described by college presidents as the number one problem on campus, and it is an important cause of death in young adults. How common is it? A survey of 10,904 randomly selected. Notice I underlined that. I'm communicating that I know that that's important. Of U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined frequent binge drinking as having 5 or more drinks in a row for 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as binge drinkers. Okay, So here is my sample size, and here are my successes. So the first thing I'm going to do, guys, before you do anything, is you're going to define your parameter of interest. And my parameter here is P. It's either going to be P or mu. Those are your two parameters. Okay? So P for this problem, and I'm going to highlight, everything is important. So like this has to be almost rubber stamp, word for word. True and all. Because that's emphasizing that this is mothership population information. So P is the true proportion of all U.S. college students who are classified as binge drinkers. So, and I have some students who get confused here for P, and they write me a sentence for N, capital N. Well, capital N would say it's just all the college students in the United States. That's not what we're doing. We are specifically talking about the proportion of all of those college students who are classified as binge drinkers. The next thing I'm going to do are my conditions. So I'm going to be random, independent, and I'm going to change this to normal again. Random, independent, and normal. Random, I'm going to put a check mark, and I'm going to put in quotes that they were randomly selected. Again, pulling that straight from the problem. Independent, I state that it's the 10% condition. However, I did not write my formula. So I'm going to come in here and write my formula. Now, my sample size was 10,904, and I need that to be 1/10 of all U.S. college students. Not all U.S. college students who drink. Little N and big N have nothing to do with what we're trying to figure out. They are just who are the people we are talking about. And we are talking about U.S. college students. P is the proportion of those who are classified as binge drinkers. But binge drinkers has nothing to do with my N's. So this is all college students. I don't know how many there are, but I'm going to assume that's okay. So I put a check mark. And he gets a check mark. Then I need to be normal. So for normal, for proportions, it's going to be your LCC. Please notice that on my NP and my NQ, the P and Q both have hats. Again, because this is sample information. So it has to go in for a P hat, not a P. So here's my N. And then I leave these P's and Q's as fractions because this cancels super nicely. Always. And then my Q is just the not version of that. So I just take 10,904 and subtract the 2,486. And that gives me the 8,418. And again, those cancel. And we are super normal. Like this is ridiculously big sample. So we're good. Okay. Now, specifically it says, all right, I want a 99% confidence interval. 99%. That's massively confident. So this interval is probably going to be a tad bit bigger than it would be if it was a 95% confidence interval, because I want to be that confident that my interval captures it. Okay, so the first thing I'm going to do is I'm going to start with my words. So I'm going to start there. When you are finding a confidence interval, I go find my formula sheet and I write that sentence, for lack of better words, out. Then so I've got it in words. Now I'm going to write it in letters. Well, my statistic here is P hat. Then plus or minus, my critical value is Z star. And the standard deviation of my statistic. Now look, I don't have hats on that P or Q. Goodness gracious. So fix that for me. P hat, Q hat over N, all under the square root. Okay? So what I have highlighted, guys, here is what I would write first. Words, then letters. Now let's put some data in here. So the P hat is from the sample, the number of people that qualified as binge drinkers over the total number from our sample. and then plus or minus. Okay, now I need a z-star. So now I'm going to go off to the side, and I'm going to find my z-star. Let's try that again. Z-star. So I'm going to draw my curve. I'm going to mark out 99%. That's going to leave 1% outside, which is going to put 0.5% on either wing. Now, 0.5%, be careful. I have students here who will put 0.05, but 0.05 is 5%. So 0.5% is 0.005. So I'm going to inverse norm 0.005 with a 0 and a 1. And you guys know that's going to give you the negative version. But you're going to go ahead and put a plus on top of that as well. And I've got my z-star here. I'm going to write it one more time back here so it's closer to the number. And again, you have to be right to 3 decimal places. And when you type that in, you're going to get 2.576. So now I can put him in there. And now I'm going to do the standard deviation. So this 0.228 came from my p hat, which is this guy. But I went ahead and turned him into a decimal. And then it's a lot easier to get the Q version, the Q hat. And then this is over my sample size. Okay, and then I want you to pause the video and go type that in just so you get the practice. And you should get a 0.218 for your low and a 0.238 for your high. So pause the video, grab your calculator, and go type that in to make sure. Okay, now that you've got your interval, now we're going to interpret that interval. And whether it specifically asks for an interpretation or not, you will always write this sentence because this is the bow on top. I am 99% confident that my interval from 0.218 to 0.238 captures the true proportion of all U.S. college students who are classified as frequent binge drinkers. So I hope you're starting to sort of feel the rubber stamp sentence that we are writing. We are 95% confident that our interval from blank to blank captures the true proportion of all whatever, who, whatever, of all beads that are red, of all South Stokes High School students who play soccer, whatever. All right, so there's a problem from start to finish. So now let's do a problem from scratch. Okay, here we go. Teens say sex can't wait. The Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. Construct and interpret a 95% confidence interval for the proportion, the true proportion of all teens who would say yes. So I have this sample, I have sample data, but now I want to sort of estimate what that means for the entire U.S. teen population. Okay? So here's what I want you to do. I want you to pause the video, and I want you to do your 3 conditions. And then once you're done with your 3 conditions, hit play. I'm going to go through mine really quickly, and then we'll go from there. So everybody pause. All right, so I need to be random. And it says random sample right there. And I need to be independent, which is the 10% condition. And my sample was 439. All U.S. teens. Check. And I want to be normal. And that's the LCC. And P and NQ have to both be bigger than 10. They're going to have hats on them because this is sample information. So 439, 246 said yes. So that's 246 greater than or equal to 10. And then 439. Let's see, the Q would be 193. All right, there you are. There are your three conditions. Okay, the next thing I want you to do, and I really want you to get in the habit of doing this before the conditions. I just kind of got ahead of myself. I want you to state your parameter. And the parameter here is P. So P is going to be the true proportion of all U.S. teens aged 13 to 17 that said, yes, they think young people should wait to have sex until marriage. So remember, P is not N. P is not all U.S. teens. P is a proportion. It's the proportion of those teens who said yes to whatever it is we're asking. So P is the true proportion of all, I'm underlining those two words because they're important. You don't have to underline them. I'm just trying to stress to you that they're important. Of all U.S. teens aged 13 to 17 who said yes, they think teens should wait until marriage to have sex. So this is kind of like the administrative stuff, the paperwork that you have to get out of the way before you get to roll up your sleeves and actually go find this interval. So we've done all the red tape. Now we get to do the fun part. So when you get here, let me add a page. All right. So when you get here, if it's, and this happens a lot, people are like, okay, I'll get done with this, and then it's, okay, I don't know where to start. Well, you're going to start with the words that are on your formula sheet. Statistic, plus or minus, critical value, times the standard deviation of statistic. And you can put those in parentheses if you want. Okay, so here we go. That's words. Now let's go in here with letters. So P hat is my statistic. Plus or minus critical value is Z star. Standard deviation is the square root of P hat Q hat over N. Normally that doesn't have hats on it, but again, I don't have population information. I have sample information. Okay, so tell you what, pause this and see if you can go all the way down to where you get your interval. So pause it, go get your interval, and then hit play. All right, so P hat is 246 over 439 plus or minus 1.96 square root. As a decimal, that P hat is 0.56. So this is a 0.44 over 439. I go to my handy dandy calculator. I type this in. I start with the minus. I type this in one swoop, and I got 0.514. And then I change it to a plus line, and I get 0.607. So there's my interval, okay? So now I want you to pause it, and I want you to try to write that rubber stamp sentence. We are 95% confident that the interval from 0.514 2.607 captures the true proportion of all U.S. teens aged 13 to 17 who said sex should wait till marriage. There we go. There's the beautiful bow on top. Okay. Good stuff. All right, here we go. I want this to be number 1. I want these to be number 2. Then find your interval. Then draw your conclusion. State your parameter first. Then do your conditions. Then find your interval, words, letters, numbers. Then write your sentence. Now, this is just what I want. If you forget and roll into your conditions and say, oh my God, I forgot to state my parameter, forgot to do number 1, it's okay to do it out of order. If it's on the paper, it's going to get graded. But your thought process should be, okay, first of all, what am I doing? And then, can I do it? And then, okay, let me do it. And then, okay, what does this mean? This is a beautiful FRQ and a wonderful example of the whole purpose of statistics. We are estimating, given the information that we have, and we are projecting a conclusion. All right. So that's the last full-blown FRQ we're going to do. I do want to let you know that your calculator can find a confidence interval for you, but I'm going to go ahead and let you know on an FRQ, you have to show it all by hand, and on the AP exam, and most of the time on my test, you're not going to have time to type it into your calculator. Very rarely are they going to ask you to find a confidence interval on a multiple choice where you don't have to show your work. But again, I want you to know what your calculator will do. Now, the calculator I have on screen right now won't show it, but I will walk you through it, and you're welcome to go mess with it and try the sex problem that we just did and see if you get the correct interval. So you're going to go to stats, and then once you hit that button, you're going to go over to tests. And you're going to scroll down until you see a 1 proportion Z interval. Then it's going to ask you for 3 pieces of information. It's going to ask you for an X, which is your number of successes. So that's the top number of your proportion. N is going to be your sample size, and then it just needs to know what confidence level you want. And then you're going to hit calculate, and boom, it's going to poop out your interval for you. Okay. Know that your calculator proportion might be slightly off from what you find by hand because your calculator is not going to round to 3 decimal places. It's going to go full out all the way through. So it's going to be more exact than what you have. But on a FRQ, they want to see your work and to see you do it by hand. Okay. All right. The last thing that we are going to talk about is determining a sample size. So if I need to be a certain percent confident, I need sometimes, once I know that, I need to know what sample size I need to include to guarantee that confidence interval. So I'm going to give a maximum margin of error. So here's what you're going to do. This is the, all right, hold on. Statistic plus or minus critical value times standard deviation. All right. This part right here is, your margin of error. So it's going to say, okay, I need the wiggle room, which is the plus or minus part. So this is your point estimate. So for your P hat or your X bar. So that's like your middle. And then you're adding or subtracting this to it. So this part right here is your wiggle room. How much above and how much below your point estimate you're going. So they're saying, okay, I need that wiggle room to be less than or equal to a certain number. So they're going to tell you what the margin of error is. And they're going to, most of the time, tell you P so you can find Q. And you're going to know your confidence level so you're going to be able to find Z. And they're going to tell you the margin of error. You're doing all of this so that you can solve for N. So again, this is not a formula that you have to memorize. You just have to know it's the back end. It's the plus or minus part of your confidence interval formula. And then you need to know how to algebraically solve this, which shockingly is where most people lose it on these problems. If they don't tell you what P, and this should have a hat on it, what P hat is, then you're going to default to 50%, which is odd, but that's what you're going to do. If they do not give you a P hat, they do not give you any sample data to put into your standard deviation, then it's going to default to 0.5 to 50%. Okay, so let's try one of these. So customer satisfaction. A company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers, but before contacting the consultant, the company president wants some idea of the sample size that he or she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion P of all his customers who are satisfied. So who would either choose a somewhat satisfied or a very satisfied on that 5-point scale, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3% at a 95% confidence level. How large of a sample is needed? Okay, so here I go. I have got, and let me add in. Give me a little bit more room. Okay, so I'm going to start with, my brain is going to go to this, statistic plus or minus critical value times standard deviation. But I'm only going to talk about these, so I'm only going to need those two. So I'm talking Z star times the square root of P hat, Q hat over N. And I want that to be less than or equal to some specific margin of error that they've given us, because this right here is the margin of error. So she's telling me that she wants it to be within 3%. So I know my margin of error has to be less than or equal to 0.03. I want to be 95% confidence. I'm going to come over here and draw my 95%. You know that anytime you inverse norm or normal CDF, you've got to draw the curve. So that's going to inverse norm. Let's see, 5% cut in half would be 2.5%. So 0.02501. And that is going to give me a Z star of a plus or minus 1.96. Now, when I do this, I'm not going to plug in the plus or the minus. I'm just going to plug in the positive version, 1.96. And then, let's see. She did not give me any sample data. Like, they didn't tell me any sample proportions. So my P hat and my Q hat are going to default each to 0.5, and I'm solving for N. Okay, so let's talk about how we're going to solve this. The first thing I'm going to do is I'm going to divide both sides by the 1.96. And the kicker here, guys, is you really don't want to do a lot of writing down. You want to leave these numbers in your calculator because you do not want to chop decimals until the final answer. So, but I'm going to write down the process, but I'm not going to write down what any of the results are. So I'm dividing. I'm going to go ahead and multiply 0.5 times 0.5. That's 0.25. Okay, and that's going to give me some number. okay? And again, I'm going to show you, we'll walk this through on your calculator, but I'm just showing you the process. The next thing I'm going to do is I'm going to get rid of the square root. So I'm going to square both sides. So now I have 0.25 over n is less than or equal to whatever that number is squared, okay? Then the next thing I'm going to do is I'm going to multiply both sides by n to get the n out of the way. So I have 0.25 less than or equal to whatever that thing is squared times n. And then to solve for n, I'm now going to divide by that guy squared. So then I have n is greater than or equal to whatever that answer is. Okay, so here I go on my calculator. All right, so here I go. I'm going to take the 0.03 and I'm going to divide it by 1.96 and hit enter. And y'all see this gives me a great big decimal, and I don't want to chop it because it's going to drastically affect my answer. So I'm going to leave him in there. The next step was to square both sides. So I am now going to square him. And I just hit the square button and it will square that entire answer. So I'm going to hit enter. Okay, and then I multiplied both sides by n, and then I'm going to take my 0.25 and I want to divide it by this number, which was the last thing I hit, the last solution that I had. So if you guys will look on your negative button at the bottom of your calculator, you have in blue, it says ANS. And so what that does is that inserts the last answer that you had. So I'm going to do 0.25 divided by that answer, and I get 1,067 point and a whole bunch of decimals. So I'm going to start by writing that down. So I'm going to go 3 decimal places. So 1067.111. So 1067.111. Okay, here's the kicker. This is asking about the how large the sample needs to be. So I'm going to put it in whole numbers. Now, a lot of people will say, well, since this is a 0.1, I should stay with 1067. But this is saying that the sample size needs to be this big. So 1067 is not going to cut it. It's not going to work. I've got to go up to 1068. And these are respondents that I need for this sample for this company to accomplish what they want. That's how many pieces of data I need to go get. So again, you're going to get a decimal, and that's fine. That's what you're supposed to get. But for multiple choice, which is what most of these are going to be, you always round up to the next number. Always round up. Now, when it's multiple choice, sometimes the multiple choice answers will be like 1,000 and then 1,080 and then like 2,500 and something else. So you're going to pick the one that's closest to what you have. Again, your answers are going to drastically be affected based on how many decimals you go. So you go exact, just like I taught you. But then I promise in the multiple choice, you're always going to pick the one that's closest to what you've got. Okay. So the last slide. In the company's prior year survey, 80% of the customers surveyed said they were somewhat satisfied or very satisfied. Okay, so I now have sample data. So this sample data is coming from last year. So I'm going to use that instead of having to default to the 0.5. Okay, so now I'm just going to redo this. So I want to be 95% confident. So I know I'm 1.96. I'm going to be the square root of 0.8, which makes my Q a 0.2. I'm looking for N, and I want to be within 3%. So tell you what, I want you to walk through this process on your calculator. You're going to divide by 1.96. You're going to square both sides. Then you multiply both sides by n, which doesn't affect your calculator. And then 0.8 times 0.2 is 0.16. You're going to do 0.16 divided by. So I want you to do the whole process and then hit play and see if you get it right. All right, so if I do this on my calculator, let's see, I'm going to do 0.03 divided by 1.96. Oh, let's get the decimal in there. Here we go. 1.96, and then I square it. And then I'm going to do 0.16 divided by that answer. 682.951. 682.951, which means 683 respondents. Okay, what if the company president demands a 99% confidence interval? So all that's going to do is that's going to change my Z. So for 99%, I need to inverse norm 1%, so 0.5%, 0.00501, and that makes my Z star plus or minus 2.576, which should ring a bell every time you do a 99% confidence level. You're going to get the same Z star. So some of these Z stars should start to kind of look familiar, and some of you might even start memorizing what some of them are. So 2.576 square root. I'm going to go and multiply my 0.8, my 0.2, and get a 0.16. So there's my setup. Again, the only thing that's different is my Z star because I have a different confidence interval. So hit pause, type this in, and get your new N. .03 divided by 2.576, square it, and then 0.16 divided by, 0.1, dang it, 16 divided by answer, 1179694. 179.694, so 1180. So here's the point of this problem. If you want to up your confidence interval from 95% to 99%, you're going to need, I don't know, looks like almost 500 more respondents. And you can subtract those and get an exact value. But if you want to up your confidence interval, then you're going to need more data. You need almost 500 more people to answer the questionnaire. Okay, I know that was a lot. I hope it sunk in, and I hope that you go back and rewatch anything that you're iffy about. I love these problems because you do this, and then you check your conditions, and then you have your formula, and you get your interval, and you write your conclusion. Like, I feel like it's so well laid out, the process, that it just really clicks with my little math mind, because I really like procedures and formulas. The kicker here is on this last part, finding the sample size. Make sure you're comfortable with why you're doing what you're doing, so you're not having to memorize something else. Because I think if you understand why you're doing what you're doing, you know which part of the formula to use. And then just make sure you're good on the algebra process for how to solve those.